You're about to see the most crystal clear explanation of the linear differential equations on the entire YouTube. There are total 4 different types that we'll learn in this video that you deal with in engineering semester 2. Let's get started. One, you immediately know that it's of the type dy by dx plus py is equal to q. How do you identify whether it is of the type dy by dx plus py is equal to q, or if it's dx by dy plus px is equal to q? This is your fx. This is your f dash of x. This is your f dash of x. Okay, and this will become your p, and this will become your q. There are 4 different types of linear differential equations that we are going to learn in this video. There are 2 more which are a little bit of extension of linear differential equation, which is the Bernoulli's linear differential equation and reducible to Bernoulli differential equation that we'll look in the next video. In this video, we are going to deal with these 4 types that you see right here. Okay, now let us start with type 1, which is dy by dx plus py is equal to q. I will just clarify here that p and q both are functions of x. So I'll just write p as p of x to make it clear that it's a function of x, and even q is a function of x. Okay, so p and q both are functions of x. Also note that the y is a dependent variable. Okay, y is a dependent variable. And x is independent variable. How do you identify whether it is of the type dy by dx plus py is equal to q, or if it's dx by dy plus px is equal to q? I've seen students getting so much confused here. It's very simple. Remember that the dependent variable occurs only once, or dependent variable is showing up only once, because p is a function of x, q is a function of x. So the dependent variable y is showing up only once with power 1. Okay, so that's why you immediately know that it's of the type dy by dx plus py is equal to q. Remember, for how to identify this dependent variable, which is in this case y is showing up only once, and that too with power 1, you immediately know that it's of the type dy by dx plus py is equal to q. In such a case, in this scenario, in this situation, the solution, in order to find solution, you first find something called as integrating factor. Integrating factor is given by e to the power integration of p of x dx. We know that p is a function of x, so I'll just write it clearly here, that integration of e to the power integration of px dx. That's how you find integrating factor. And then the solution, you write it as y into integrating factor. Y into integrating factor is equal to integration of q into integrating factor with respect to x. Because remember, q is a function of x, and even integrating factor is a function of x. So we integrate with respect to x and add a constant of integration c. That's the solution of this differential equation dy by dx plus py is equal to q. I hope this makes sense. One other thing which I want to highlight over here is, remember that this y into integrating factor, this y was a dependent variable. Okay, y was a dependent variable. Why am I telling this again? Because it is always dependent variable into integrating factor. Whatever the dependent variable, you multiply that with integrating factor always. Okay, that's always the case. All right, now let's move on to next type, which is our dx by dy plus px is equal to q. Okay, here if you notice, x is the dependent variable. And it occurs only once with power 1. Okay, the dependent variable, which is x, it show up only once, and that too with power 1. If that happens, you immediately now know that instead of y, now x is the dependent variable. And obviously here p is a function of y and q is a function of y. It's exact same approach. They have just switched the variable names. Okay, and students get so much confused here. Okay, the solution is also similar here, like we found before. We first find the integrating factor, which is given by e to the power integration of py dy. Remember that p is a function of y now, so you integrate that with respect to y. And the solution, the way you write, remember that in the previous case, we wrote it as dependent variable into integrating factor. So here we will write x into integrating factor is equal to integration of q into integrating factor dy plus c. Because my dependent variable here is x, which is why I write x into integrating factor. In previous example, in the previous type, y was my dependent variable, so I write y into integrating factor. But here my x is the dependent variable, so I write it as x into integrating factor. Okay, so remember, x is my dependent, x is my dependent variable. So you always write dependent into integrating factor is equal to integration of q into integrating factor. Remember here q is a function of y, and even integrating factor is a function of y, which is why we integrate this with respect to y, and that's your solution. It is such a simple thing. Now let's try to solve some examples of type 1 and type 2, and then we'll come to type 3 and type 4. All right, let's solve this example. If you notice here, y is the dependent variable. The way we know that is dependent variable is occurring only once, that too with power 1 over here. That's why we immediately know. Therefore, this is of the type dy by dx plus py is equal to q. We immediately know that it's of this type, where p is 4x upon x square plus 1 and q is 1 upon x square plus 1 the whole cube. We found p and q which are function of x. In order to solve this, we find something called as integrating factor. Integrating factor is e to the power integration of p dx. Okay, so integrate p with respect to x in the power of that exponential. So which is how you get e to the power integration of 4x upon x square plus 1. 4x upon x square plus 1. You can either do method of substitution here in order to integrate this, or we can just use the standard result. Remember, whenever there is integration of f dash x upon fx, integration of f dash x upon fx. So there is, if the derivative is in the numerator and there is a function, the result of this is log mod fx or log fx, whatever you call it. Okay. So if derivative is in the numerator and the function is in the denominator, the result is log fx. So the way you get here is integration of, if you notice the denominator derivative is 2x, okay, derivative of x square is 2x and derivative of 1 is 0. So the derivative of denominator is 2x and here there is 4x. Let us take 4 out and just write it as 2x over x square plus 1 dx. Now, if you notice, this is exactly f dash x over fx, because this becomes your f dash x and your denominator becomes fx. Your denominator becomes fx. So immediately now you can say this is e to the power 2 times f dash x upon fx. Result is log mod fx. So this is 2 times log of x square plus 1, log of x square plus 1. Okay, I hope that makes sense. Now using the property of the log, you can send this 2 in the the power here of power of log. Okay, this 2 can go on the top here. So that will give you e to the power log x square plus 1 the whole square. Okay, and again we'll use the property of log, another property of log. Remember, this is natural log. Okay, remember this is natural log. So the base of the log is e because it's a natural log. And because the base of the log is e, we know the property of log that if there is a variable a and if you have log to the base a x, this is nothing but x. If this base of the log becomes equal to this number here in the base, the result is just x over here. Okay, so here this e and this e are same. So the result will just be this part, x square plus 1 the whole square. So that's the result that you get. So your integrating factor is x square plus 1 the whole square. I hope that makes sense. Now we can just write the solution. We can just say that solution is given by y into integrating factor. Remember, it is always dependent variable into integrating factor. That's how you remember it. Dependent variable into integrating factor is equal to integration of q into integrating factor dx plus c. That's your solution. And integrating factor we already found. So we have y into integrating factor is x square plus 1 the whole square is equal to integration of q. What's the value of q? 1 upon x square plus 1 the whole cube. So 1 over x square plus 1 the whole cube into x square plus 1 the whole square dx plus constant of integration c. Now this x square plus 1 the whole square and this cube will get cancelled. So you'll be left with power 1 in the numerator, the denominator. Okay. So therefore you get y into x square plus 1 the whole square is equal to integration of 1 over x square plus 1 dx plus c. Now we know this integration 1 over x square plus 1, this is nothing but tan inverse of x. So therefore, y into x square plus 1 the whole square is equal to, this is tan inverse of x. Okay, integration of 1 over x square plus 1 is tan inverse of x plus c, and that is the solution that we are looking for. I hope that makes sense. This is such a beautiful question that we are solving right now. If you notice this differential equation that we need to solve, y is occurring multiple times in multiple places, but x is occurring only once with power 1. Okay, x is occurring only once with power 1, occurs once with power 1. What that tells you is whatever occurs with power 1 just occurs once with power 1 is your dependent variable. Okay, so your x in this case is a dependent variable, is what we are able to conclude so far. Dependent variable. Since x is occurring only once and it's a dependent variable, we need to convert it in the form dx by dy plus px is equal to q. So we need to convert it in the form dx by dy plus px is equal to q. That means we want dx by dy separate. Okay, if you want to separate dx by dy, we have to divide the entire equation by 1 plus sine y, because dx by dy we want to separate. Okay, so you have 2y cos y, 2y cos y divide by 1 plus sine y minus x and sec y plus tan y divide by 1 plus sine y. I hope that makes sense. Now let's bring this term with x on the left hand side, just like we have in this dx by dy plus px. So therefore we have dx by dy plus x times sec y plus tan y divided by 1 plus sine y is equal to 2y cos y divided by 1 plus sine y. Okay, now this is of the form dx by dy plus px is equal to q. That tells you that this whole thing is p and this whole thing is q. So therefore we have p is equal to sec y plus tan y divided by 1 plus sine y, and your q is 2y cos y divided by 1 plus sine y. Now let's try to find integrating factor. We know that integrating factor is given by e to the power integration of p dy, because p is a function of y now. So it's integration of e to the power integration of p dy. Let's try to find integration of p dy first. Okay, since it's a bigger function, just let's find it separately. So we say integration of sec y plus tan y divided by 1 plus sine y and with respect to y. How do we integrate this? I see the best approach that I can see is convert everything into sine and cos. So what we can do is we can just write this sec y as 1 upon cos y. This tan y, I can write it as sine y upon cos y and divide by 1 plus sine y. So we just convert everything into sine and cos. Now in the numerator, what I can have is integration of this denominator is same, so the numerators get added. So I have cos y and I have 1 plus sine y divide by 1 plus sine y and I have dy. Very easy so far. Okay. Now if you notice this 1 plus sine y and 1 plus sine y will get cancelled. So basically you are left with integration of 1 over cos y dy, which is nothing but integration of sec y dy, sec y dy. Now we know by formula integration of sec theta or sec y is log of sec y plus tan y. Log of sec y plus tan y is, we found that integration of p dy. So we found the integration of p dy already. Now we can substitute that integration in our integrating factor. We can substitute that in our integrating factor. So our integrating factor will become, therefore, our integrating factor will become e to the power log of sec y plus tan y, log of sec y plus tan y. Now, since it is natural log with a base e, natural log always has the base e, we can use the property of the log, okay? This log and e terms will get kind of cancelled and you are left with sec y plus tan y, which is your integrating factor. Now, since we have integrating factor, let's write the solution. Let's try to write the solution. We know that solution is now dependent into, so remember, solution is always dependent variable into integrating factor. In this case, dependent variable is x. So we write x into integrating factor is equal to integration of q into integrating factor. And remember, q is a function of y, integrating factor is a function of y. So we integrate with respect to y and plus c. Now let's substitute the values that we have. So we have therefore x into integrating factor is sec y plus tan y is equal to integration of. Let's substitute the value of q. What's the value of q? So the value of q is 2y cos y upon 1 plus sin y. It's 2y, q is 2y cos y divided by 1 plus sin y into sec y plus tan y. Sec y plus tan y. And this is dy plus constant of integration c. It's not that hard to integrate this. We just have to convert this into sine and cos. We just have to convert those variables or those trigonometric functions into sine and cos. So we have 2y cos y divided by 1 plus sine y. And let's write this as this sec y is 1 upon cos y, 1 upon cos y plus this tan y is sine y upon cos y. This is dy plus that constant of integration c. Let us simplify this a little bit. This will become integration of 2y cos y divided by 1 plus sine y. The denominators are same, so we can just add up the numerators. So we'll get 1 plus sine y divided by cos y into dy plus c. If you notice, this 1 plus sine y and 1 plus sine y will get cancelled. This cos y and this cos y will get cancelled. So basically you are left with integration of 2y dy plus c. 2y dy plus c. Now this can be written as 2 is constant, can come out of integration. So you can just write 2. Integration of y with respect to y is y square divided by 2, because this is y to the power 1. So we get y square divided by 2 plus c. And in the left hand side, we have x into sec y plus tan y. And that's your solution of differential equation that we are looking for. All right, let's look at next type, which is type 3 and type 4, which is reducible to linear differential equation. So the differential equation that will be given to you will not be linear by default. You will have to just do a small thing and convert it to linear. Okay, let's see what do we mean by this. So the original form that we know is dy by dx plus py is equal to q form. That's the original linear differential equation form in y, because y is the dependent variable. Now instead of y, they can give you fy. But when they give you fy instead of y, they will also give the derivative of the product of dy by dx. Okay, so instead of y, they will give you fy and they will also give you derivative of f dash y. It's just like saying the derivative of y, which was 1, which was present here always, and we did never noticed it. Okay, so just like in linear form, the derivative of y was present here. We can have fy and there could be f dash of y here. Okay, in order to solve this, or in order to convert it to linear, we call it reduction to linear. We can reduce this differential equation to linear by just saying this fy function. We can just say that fy is equal to t. We can just say fy is equal to t. And when you put that fy as t, differentiate this equation with respect to x, differentiate this fy is equal to t with respect to x. Okay, so if you differentiate with respect to x, derivative of fy with respect to x is f dash of y into derivative of y with respect to x, which is dy by dx by chain rule, is equal to dt by dx, derivative of t with respect to x. Okay, here I applied chain rule to say this derivative is f dash of y and derivative of y is dy by dx with respect to x. Okay, so we can make that substitution here. So this f dash of y dy by dx is dt by dx. So I can just say this is dt by dx plus p times t. This is t. Okay, I'm making the substitution. Fy is equal to t is equal to q. So that is now linear in t. This is linear differential equation in t. Notice that now t occurs only once with power 1, which is why it is linear in t. The other type, which is type 4, is very similar to the form dx by dy plus px is equal to q. Why it is similar? Because instead of x, here we have fx, and instead of 1 over here, we have function derivative of fx, which is f dash of x. Okay, you can convert it to linear. You can reduce this equation to this type by saying put fx is equal to t. Put fx is equal to t. So you put fx is equal to t. Remember that now we are differentiating with respect to y, okay? Because we want dx by dy. So we'll differentiate this with respect to y. This is very important step, okay? I have seen students make mistake here. This is very important step. Note this. Now if you differentiate this with respect to y, derivative of fx with respect to y is f dash of x into dx by dy. So you differentiate this and you take derivative of x with respect to y by chain rule is equal to dt by dy is equal to dt by dy. Now we can make that substitution over here in this equation, and therefore we get dt by dy plus p into t, because this fx is now t, is equal to q. Now remember that this is a linear differential equation in t. Linear in t, because t is your dependent variable now and y is your independent variable, which is why it is always helpful to look it as dependent variable and independent variable rather than just looking at it as x and y. Always call it dependent and independent. Okay, that will just make your life so easy. Now let us look at some examples of reducible to linear form. Now let's solve this example. Y divided by dx plus 4x divided by 3 minus y square over 3x is equal to 0. Okay, this is not of the type linear because there is not a single variable here that occurs only once. Okay, there is x which occurred 2 times and even y occurs 2 times. But if you notice the derivative of y square, the derivative of y square is 2y, but there is no 2, but there is y present. Okay, so the derivative of y square is easily manageable over here. Therefore, it is of this type. Therefore, because there is derivative, because there is fy and there is f dash of y. Okay, so it's of this type: f dash y dy by dx plus pfy is equal to q. So let's see. Let's take q on the other side. So x is our dependent variable. Let's take 4x plus divided by 3 on the other side. So therefore, we have y dy by dx, y dy by dx minus y square into 1 over 3x is equal to minus 4x divided by 3. I hope that makes sense. Now we can convert this to linear by putting y square is equal to t. Why do we put y square is equal to t? Because the derivative of y square is present over here. Okay. Always remember that we have to differentiate this always with respect to independent variable. In this case, independent variable is x. So we differentiate this with respect to x. Differentiate this with respect to x. Even here, remember, we always differentiate with respect to independent variable. Here, independent variable is y. We always differentiate with respect to independent variable. So if you differentiate with respect to x, derivative of y square with respect to x, it is 2y into dy by dx. 2y into dy by dx is equal to derivative of t with respect to x is dt by dx. The term that I'm looking for here is y dy by dx. So y dy by dx here is given by y dy by dx. You can just divide by 2 here. So you'll get half dt by dx, because that's the term I'm looking for, y dy by dx. Okay. So therefore, I have here y divided by dx is half dt by dx. Okay. So therefore, you can make that substitution now. So therefore, you can eliminate y from here and convert it to t. So this y divided by dx is half dt by dx minus y square is t. So this is t times 1 over 3x is equal to minus 4x divided by 3. Now, if you notice, this is linear in t. This differential equation is linear in t. Why is it linear in t? Because t is occurring only once with power 1 now. Okay, so you can easily solve it by linear in t concept. Okay, just let's remove this half from here. So multiply by 2. So therefore, we have dt by dx. Just multiply entire equation by 2 minus t into 2 divided by 3x is equal to minus 8x by 3. Now this is of the form dt by dx plus pt is equal to q. Okay, dt by dx. This is just like dy by dx plus py is equal to q. Okay, where where p is equal to minus 2 over 3x and q is equal to minus 8x over 3. Now we can just solve it like we did for linear. Let's quickly solve it. Let's first find integrating factor. Integrating factor is e to the power integration of p dx, okay, which is equal to e to the power integration of minus 2 by 3x dx. Okay, so which is now equal to e to the power. This minus 2 by 3 is constant and can be taken out of integral. So this is minus 2 by 3 integration of 1 by x dx. So that will become e to the power minus 2 by 3. Now integration of 1 by x we know is log x. This will become log x. All right. Now this is equal to e to the power. Now this minus 2 by 3 using the property of log can be taken in this power. Okay. So that will become log of x to the power minus 2 by 3. Log of x to the power minus 2 by 3. Also remember that this is a natural log and natural log has the base of e, which is why this log term and this e term, this whole thing will get cancelled and you will be left with x to the power minus 2 by 3, which is your integrating factor. All right. Now that we know integrating factor, our solution is dependent variable into integrating factor. Always remember the solution is always dependent variable into integrating factor. In my case, dependent variable is t into integrating factor. Why is it t? Because our differential equation, linear differential equation was linear in t. So t is my dependent variable. Okay, so it's t into integrating factor is equal to integration of q into integrating factor. Okay, dx plus c. Because my q is a function of x and even integrating factor is a function of x. Q is a function of x and integrating factor is a function of x, which is why I integrate with respect to x. So therefore, remember t is nothing but y square. T is y square is what we had made substitution. If you remember, if you just look above here, we just put y square as t. Okay, so that's what the substitution that we made. So we can resubstitute back now. So y square into x to the power minus 2 by 3 is equal to integration of q into integrating factor. So q is what? Q is minus 8x by 3. Q is minus 8x by 3 and integrating factor is x to the power minus 2 by 3 dx plus c. Okay. So therefore, y square into x to the power minus 2 by 3 is equal to this minus 8 by 3 is constant, can be taken out of integration of, and here we can just apply the law of indices. So this is x to the power 1 times x to the power minus 2 by 3. We can just write this can be just written as x to the power 1 minus 2 by 3 by the law of indices. Okay, if the base is same, the power gets added up. So this will become x to the power 1 by 3. Okay, So we can just now complete our integration. This is very easy now. Y square into x to the power minus 2 by 3 is equal to minus 8 by 3. Now integration of x to the power 1 by 3, this is just like x to the power n. So the integration is x to the power 1 by 3 plus 1 divided by 1 by 3 plus 1 plus c. Okay, using the formula of integration. So therefore we have y square into x to the power minus 2 by 3 is equal to minus 8 by 3 x to the power 1 by 3 plus 1 is 4 by 3. Okay, divide by 4 by 3. Okay, plus c. Now this 3 is in the denominator and this 3 is in the denominator's denominator. So both can get cancelled. This 4 can get cancelled with 8 and you will be left with 2. So therefore you have the result. Therefore you have y square into x to the power minus 2 by 3 equal to minus 2 into x to the power 4 by 3 plus constant of integration c, and that is the solution that we are looking for. I hope that made sense. All right, let's look at this next example, another beautiful one that will use all the concepts that we have been studying. If you notice this equation, is it linear or not? Let's first find that out. Is x occurring only once? No, x is occurring once here or twice here and twice here. So it's not occurring once. Even y is occurring multiple times. Okay, y is occurring 2 times here. So this is not a direct linear, but we'll have to reduce it to linear. Okay, now in order to reduce it to linear, we have two options. We can either have f dash y dy by dx plus p of fy is equal to q, and the other option we have is and f dash x dx by dy plus p into fx is equal to q. So these are the two options that we have studied and that we have. Okay, let's see which type it is. If you notice, fy derivative is present, fx derivative is present. Is there a function whose derivative is already present over here? Okay, let's look at it carefully. So if you notice this part, x into e to the power x, if you notice this, the derivative is somewhere this function. Why is this? Let's see. If you look at that x e to the power x, x e to the power x, let's take derivative. Okay, let's take derivative of this. You have to apply product rule in order to differentiate this. The derivative is, so you keep, this is just like u and v. So u derivative of v, so x into derivative of e raised to x is e raised to x plus u v as it is, e raised to x, derivative of x is 1. This is just like product rule or UV rule of derivative. So you get e to the x common, x plus 1. So if you notice this, if this is your fx, this is your f dash of x. So somewhere it is of this type because you have fx present and f dash of x present. It's a very good question. Okay. So since you have it's of this type, you need to convert, you need to first find dx by dy. You need to first find dx by dy here. So in order to find dx by dy, let's just shift this term on the right hand side. So therefore, I have e to the power x, x plus 1 into dx is equal to minus of, or if you shift it on that side, just the signs will change. This negative will become positive, x e to the power x, and this positive will become negative, y e to the power y times dy. Okay, that's the situation that you have. I'll just make a partition over here. All right. So therefore, here we need to find dx by dy because we already identified is of this type. So we get dx by dy is equal to x into e raised to x minus y into e raised to y divided by e raised to x into x plus 1. Okay. Now, since we have dx by dy, in dx by dy, we need f dash of x, which was this function here. So we have to multiply this function on this side now. So therefore, we have e raised to x into x plus 1 into dx by dy is equal to x into e raised to x minus y into e raised to y. Okay, I hope it's making sense so far. So therefore, I'm just trying to convert it to this type. Okay, so I have f dash x dx by dy. Now I need p into fx. I need p into fx is equal to q. Okay, fx fx was this function, fx was x into e raised to x, right? Because this was fx. So fx was this. So I need this on the left side. So I have e raised to x into x plus 1 into dx by dy minus x into e raised to x is equal to minus y into e raised to y. Okay. Now this is of the type this f dash x. So this is f dash x plus p into fx. So you see fx is equal to q. Okay. So therefore, in order to solve this, remember that if you want, there is a plus here, you can actually make it look exactly like this just by doing like this. Dx by dy plus minus 1 into x into e raised to x is equal to minus y into e raised to y. So what happens by doing this is just exactly of the form p into fx. Okay, this is exactly of the form p into fx. So this is your fx. Remember, this is your fx. This is your f dash of x. This is your f dash of x. Okay, and this will become your p and this will become your q. I hope that makes sense, that how we converted it to this type. Now, since we converted to that type, we can solve this by doing put fx is equal to t. We can just put fx is equal to t. So therefore, we put x into e raised to x as t. We put x into e raised to x as equal to t. So we get x into e raised to x. So differentiate this with respect to, we always differentiate with respect to independent variable. Independent variable here is y. So differentiate this with respect to y. So therefore, let's apply UV rule here. Okay, UV rule. So x the way it is into derivative of e raised to x is e raised to x plus e raised to x the way it is, derivative of x is 1. Okay, and then we have to also do dx by dy by chain rule. We also have to multiply, since we are differentiating this with respect to y, we also have to write dx by dy by chain rule is equal to derivative of t with respect to y is dt by dy. Okay, dt by dy. So now you can see that therefore you can take e raised to x common here, e raised to x into x plus 1 into dx by dy is equal to dt by dy. So we have this replacement of this. This whole thing is now dt by dy. So therefore, dt by dy plus minus 1 times this is fx, which was t times t is equal to minus y into e raised to y. Minus y into e raised to y. All right, now this is of the linear form where y is independent and t is dependent. So we find integrating factor by saying e to the power integration of p into d. Okay, now remember that p and q both are function of independent variable. Okay, p and q are both functions of y. Okay, don't make a confusion here because it's p, the value of p is minus 1 over here. So you don't easily see that if it's a function of y. But remember, in this case, p and q both are function of y because y is dependent variable. Okay, p and q are both always functions of independent variables. So e to the power minus 1 integration of minus 1 dy, which is e to the power integration of minus 1 is y. Okay, integration of 1 is y and this minus. Okay, and that's your integrating factor, e to the power minus y. Okay, now the solution is, now the solution that you can get is always dependent variable into integrating factor. Solution is always dependent. In this case, dependent is t. So t into integrating factor is equal to integration of q into integrating factor into dy plus c, because q and integrating factor both are functions of y. So we integrate with respect to y. Okay. And remember that t was x into e raised to x. T was x into e to the power x. So you can substitute that back. So therefore, x into e raised to x. Integrating factor is e to the power minus y is equal to integration of q into integrating factor. What was q? Here that q is minus y into e to the power y. So minus y into e to the power y. Integrating factor is e to the power minus y dy plus c. So we can just substitute the value of q, which is this integrating factor, which is this here. Okay, from here. All right, now let's just quickly write it down. So therefore we have x into e to the power. Now here, since the base is same, the power will get added up. So this will become x minus y equal to integration of. Now e to the power y, this e to the power minus y. Okay, so e to the power minus y is just like 1 over e to the power y. So this and this will get cancelled. So you have integrate, this minus can be taken out, y dy plus c. So therefore you have x into e to the power x minus y is equal to minus y square divided by 2 plus, so integration of y to the power 1 is y square divided by 2, and that's your solution that we are looking for. Such a beautiful and important question it is for Mumbai University. Okay, I hope that made sense.